Okay, so as I said, the slides are available right there. My name is Ariel, Rokem. I'm a data scientist at part of the university called the eScience Institute. And I'll tell you a little bit about the eScience Institute because that context in which I'm doing this work is important, I think. The Institute is interdisciplinary and it's focused on data science, very broadly construed. And we do different kinds of things. We do data science education, that'll be sort of the focus of this talk, but we also work ourselves on the development of tools and practices very much focused on reproducible research and the practices for reproducible research. And then we're involved in building a data science community on our campus and around the world, data science community that is open, rigorous, and ethical. And then we do our own data-driven research. And when you think about data-driven research, traditionally people think of these kinds of instruments on the left from astronomy, the Sloan Digital Sky Survey, on the right there, the Large Hadron Collider. And these are big instruments shared by a research community that produce masses of data, data tsunami, as Bill said before. And these kinds of instruments have brought rise to the idea that there's a different paradigm of scientific discovery that follows on these paradigms. So we started with empirical research, sort of like Galileo Galilei looking at the sky or dropping balls off the Tower of Pisa. And then we added on that theoretical mathematical formulations, maybe think of Maxwell's equations, things of that sort. And in the 20th century, we could already simulate rather complicated systems, so think of sort of simulations of finite element models. And then Jim Gray proposed, who was a computer scientist who worked with researchers that had a lot of data, suggested this idea that there's a fourth paradigm, data-driven scientific discovery, that when we have these kinds of data sets, like the kind of data sets that the astronomers have, that the high-energy physicists have, the data start telling us things just by virtue of their massive size. And we're entering a phase of research in which data-driven discovery is affecting all fields. So I'm particularly interested in brain networks, these brain networks in the white matter under the cortex, and our ability to make inferences about the role of different parts of the white matter on behavior. And I'm using diffusion MRI data in humans. And we're entering an era where there are masses of data for me to work with. So we're entering something I'm calling the era of brain observatories, these kinds of large projects like the Human Connectome Project or the Healthy Brain Network that produce on the order of thousands of data sets with thousands of individuals and measurements from their brains. And another one is the ABCD project, also with thousands. And finally, the UK Biobank, which will have on the order of hundreds of thousands of individuals recorded with data that we can then go and analyze at this scale. And when we start analyzing data at this scale, we might hope to do data-driven discovery. And this presents tremendous opportunities. These new data sets will enable important new discoveries on a variety of different things that we're interested in knowing about the brain, primarily through this fourth paradigm, the data-driven discovery. But there are, of course, tremendous challenges. There are the technical challenges that a lot of us work on here in this community. There are conceptual challenges about sort of understanding what it means. Are we measuring things at the right scale? The kinds of things that people who spoke at the session this morning are wrangling. And today's talk will focus mostly on the socio-technical issues that we face. So what are socio-technical issues? These are issues like how we collaborate in our research, how do we publish our results, and how we train the next generation of researchers. And first, I'd just like to point out that this kind of data calls for new models for collaboration. And one primary mode that we can collaborate is through open source software. And I think of open source software as an important complement to these big open data sets. And don't take my word for it. This is from a recommendation from a report to the National Academy of Sciences in the US that funding agencies should focus on open source usable tools and infrastructure to support reproducibility as a goal. And that's really a valuable goal and provides a basis for thinking about open source software. I work primarily in Python. Python provides an excellent ecosystem for scientific computing because it's free, it's open source. It's a high-level interpreted language, so it's relatively easy to pick up and has a very wide adoption. For example, in astronomy, That green line there, so the x-axis here is years, and the y-axis here is the percent of refereed publications mentioning these different software tools, and you can see that Python has really taken off after 2010 as a really important tool in this community. And that's because Python has an ecosystem of tools around it. So initially tools for numerical computing, tools for interactive computing like Matplotlib and Jupyter. And then people developed on top of that tools to do a variety of different things like machine learning and high-performance computing and image processing. And out of that grew various sub-communities in different fields, like in biology, in astronomy that I've mentioned before, and in neuroscience, in neuroimaging, the NiPy community, neuroimaging in Python, that developed a whole host of a family of different software tools. And there are other tools in neuroscience. I'll just mention tools from the Allen Institute that are written in Python. But in parallel, developments happened in industry using also Python, tools like Pandas that analyzes tabular data, tools for high-performance computing that are very common in industry, and then tools for machine learning and artificial intelligence that were developed by the companies that use these kinds of ideas in their own products. And then these tools all interoperate very well with other open source software languages like R and Julia. And within neuroimaging, as I mentioned, there's a whole community around open source software. Neuroimaging in Python is the community where I work. We think of this as a community of practice rather than being a single project with sort of a clear hierarchy and leadership stemming from a particular research group. It's a community of individuals working and sharing practices. And there are many different projects. I work in particular on diffusion imaging in Python, and we think of it as a comprehensive, thoroughly tested, well-documented software tool for doing diffusion imaging that people can use and can collaborate. So the question is, do neuroscientists use Python? We saw that astronomers do, and so here are curves that are similar to the curves that I showed you before. On the left here is actually general usage of, this is an index of the popularity of programming languages based on Google searches, and you can see just in general, Python has had a huge rise in popularity, but in biomedical research usage, both as indexed by mentions of Python in PubMed and also specifically in neuroimaging, there hasn't been quite that rise that we've seen. And the question is maybe why that is. And I think some of that has to do with the way that a lot of our trainees feel, which is that they get thrown off the deep end into the tsunami, and they have to sort of figure things out. So training, there's a gap in the training, and we need to think about how we cover that gap between the 20,000 feet and the 2-foot view. How can we get more people involved in open source? How can we get more people using these tools to do their research? In particular, when the methods are really rapidly changing. So even, as a lot of you know, just staying abreast of developments in these software tools is really hard, even if that's the focus of your work, let alone if the focus of your work is to do research on a particular model system. And learning these tools often requires substantial hands-on experience with the tools. And so there are different kinds of solutions to this. Bill mentioned the Carpentries before, and I'll mention this again. This is an organization that organizes these 2-day workshops focused on computational skills that anyone can invite to their campus to give either what's called a software carpentry or a data carpentry workshop, either focused on basic software engineering or on data management skills. And these are done really at the 2-foot level. So it begins with the assumption that people in the room don't know anything about these tools, and starts by showing them what are the lines of code that they should be typing in on their own computers. And that's very practical and very, very useful. Another completely different approach is one that I'll focus a little bit more on is science hackathons. And one example of that is the brainhack.org hackathons that take place at the OHBM conference. It's based on sort of this idea of the hacker ethic. This is a list taken from this book by Levy, writing about hackers in the 1960s and 1970s, mostly around the northeast part of the US. So the ethos goes that the access to computers and anything which might teach you something about the way the world works should be unlimited and total. always yield to the hands-on imperative. So this idea that you should be doing things with your hands, that computational skills are not just this theoretical thing to write on the board, they're a thing to do with your hands. All information should be free. Mistrust authority, promote decentralization, and you can see that a lot of the open source software projects espouse that kind of idea. This is the idea of something about meritocracy that is espoused. Hackers should be judged by their hacking, not criteria such as degrees, age, race, sex, or position. So anyone can hack. And you can create art and beauty on a computer. Sometimes you do things not for the reason necessarily of understanding, but to create things that are pretty. And then computers can change your life for the better. And we see that all the time with students that we work with, of course. And maybe that should be a major goal of training, is to make people's lives better. But hackathons often also suffer from this gap. If anyone here has been at a hackathon, you start by offering an idea for what you would do. And how would you know what to do if you don't know what's possible? And so we're trying to bridge that gap to get people hacking through a model that we call Hack Weeks. And this is a model that I shamelessly stole from the astronomers. I saw Daniela Huppenkotten and my colleague Jake Vanderplas were organizing an Astro Hack Week at my institute, and so this is the interdisciplinary context. I saw it and I thought that just looks so much fun. I should do something like that in the neuro domain, and that's that I organized as a Hack Week. The idea behind Hack Weeks is they're week-long events, so they're pretty long in their scale, and they combine tutorials, lectures, and project work to bridge that gap between people who don't know how to program at all and people who want to start hacking. And they balance between pedagogy and hacking, and depending on the discipline, the exact discipline that you're working in, you might need more focus on pedagogy here on the y-axis or more focus on projects and hacks. So for example, the astronomers usually come with a stronger background in programming, so they might be closer to this focus on projects and hacks, and we might be a little bit closer, in some cases in neuroscience, we might be closer to a classic summer school or a software carpentry workshop. And so one really important focus of all these events across different domains, both in astronomy, in neuroscience, in geosciences, there's also GeoHack Week now, and there are several others that have arisen from that, is an explicit focus on diversity and inclusion, including people that otherwise wouldn't be participating in hackathons if we didn't make it an explicit effort to include them. So NeuroHack Week, we started NeuroHack Week, and by we I mean myself and Talia Arconi from UT Austin, who is my co-organizer in this. And we did one event in 2016 and another event like that in 2017, having 40 participants each year. The first day was focused on lectures and tutorials, bringing people into the language and the tools. And then the rest of the days had hackathons and breakout sessions organized by the participants. It was pretty free form, and people did fantastic things. And we thought we can do more than that. And so we wrote a grant, and this event in 2018 started and is going to go, thanks to the funding that we have from the National Institute of Mental Health, until at least 2021, called Neuro Academy. That's a summer institute in neuroscience and data science. And it's 2 weeks now, and we have 60 participants each year. So it turns out you can make this longer. The first week is, again, focused on lectures and tutorials. So we could do a lot more with a full week of lectures and tutorials on various data science tools, programming, version control, cloud computing, and lectures by researchers, instructors who use data science tools in their own research, whether it be about brain networks or about topological organization, topographic organization of the brain anatomy, or implementation of software tools. And then the second week is a 5-day-long hackathon where participants just propose projects and then set to do those projects, coming up with various creative ideas, and then organize into groups. And so this is what that looks like then. You're seeing here folks sitting and hacking. You see Kirsty, who is a participant in the first NeuroHack Week, really enjoying herself there. You see Anisha Keshavan, who is a postdoc with me, with a group of people sort of teaching them something in a less formal setting where people are with their hands on the keyboards. And then, of course, people having discussions around a whiteboard about something and socializing with each other and creating sort of a community and a network around this. And you can go and see, we actually just wrapped up Neuro Academy 2019 just a few weeks ago, and you can go and see what kinds of projects people do in this context. It's a variety of different things ranging from data visualization to analysis of data to implementation of software. And the range is really big, and it's really, really impressive to see what people can achieve within the scale of 5 days. Now, we wanted to know what people think after they do this. So here we have a comparative analysis. We did the same survey in 3 different events: astronomy, geosciences, and neurosciences. And we asked questions like, I feel like I learned things which improve my day-to-day research. And that high green bar there is that those people strongly agree with that statement. So it seems to be that this kind of event teaches people things that are highly practical to their day-to-day, which is great. They also feel like they become better scientists for the most part, and that they feel like they build valuable connections, which is an important part of creating a community of practice around these tools. And then a variety of other things that I think you can see here seems like this is a successful event. So let me just, before I wrap up, just speculate about why I think this approach is effective. The first idea is this idea of active learning, which some of you, or a lot of you might be familiar with, the idea that by doing, you can learn. I think this is particularly important for topics where practice and skills are important when you come with the particular knowledge. It's known now that active learning is particularly good when the people learning are not complete novices. And so we actually require that the people coming know something about programming and something about neuroscience. I don't think this is necessarily a great approach to start an undergraduate curriculum with. The second idea is the idea of legitimate peripheral participation. And this comes from the sociology of sort of social context of learning. The idea is that people can become part of a community of practice and learn within a community of practice by doing small peripheral tasks that are legitimate, that are actually authentic activities. And so one of the things that happens in Neuro Academy is that several of the participants make their first contributions to an open source software project in the context of the Neuro Academy. And that is because we have a fantastic set of instructors, and many of them are involved in the open source software projects that I mentioned before, and so they can guide the contributions of the individuals within this context. And so this idea of legitimate peripheral participation is an idea about how people learn within a community. And then finally, a little even more speculative is this idea from this philosopher Hakim Bey of the temporary autonomous zone. And this stems from my idea that education, training should be about making people more free, more liberated. And so one way to give people liberty is to create a temporary zone where they are completely autonomous, where they are freed from the burdens of their day-to-day in the lab. Often, researchers in PhD or a postdoc can be quite stressed out by the demands of their programs. Here, we're putting them in a situation where we tell them, don't do anything that's useful for about a week. Just do things that you enjoy, that you're interested in learning from. And so I think this temporary autonomous zone gives them a place to grow. And I think that's really effective and liberating. And I think people really enjoy that and grow out of that. And so before I end, I'll just like to thank, first of all, Talia Erconi, that I mentioned before, and Jane Ko, who is co-organizing this at the University of Washington eScience Institute. Daniela Huppencotton is the astronomer that I mentioned before. Anthony Arendt organizes Geo Hack Week, and discussions with both Daniela and Anthony were really, really useful to me in thinking about this. And then finally, the amazing team of Neuro Academy instructors that we have and the participants who come and really participate in this. And I'd like to thank all these sources of funding, and I'd be happy to answer any questions you have.